Okay, I hope everybody can hear me. I think I've got it turned on right. And today we are going to continue our discussion on chapter 24, the metabolism chapter, which probably isn't really 24, but we'll just call it that. And we had wrapped up the other day talking about carbohydrates. Now, there is not going to be a lab test before spring break. There won't be a lecture test before spring break. I've had questions on both of those. Yes.
When do you think the next lecture test will be?
After spring break. That's the best I can say.
Would it be like a week after spring break or like a little bit longer?
Well, I have to give you you have to have your bone test. Because we're going to wrap up bones today with joints and articulations. And so it would be cruel and unusual to ask you to take your bone test immediately after spring break. So I may push that back a little bit. Depends on if I finish this week. Because if I finish chapter 24 by Thursday, we could have a test on the Thursday after spring break. That would give you plenty of time to get ready. It's not like coming back, hey, welcome back from spring break, here's your test. And it would still allow the bone test to be the following week. So the earliest lecture test we could have would be the Thursday after spring break. So that would give us time to get back into it and start chapter 6. So lab, I will finish joints and articulations today. It's very short. And my plan for lab is to do joints and articulations and then introduce you to skeletal muscles. Muscles will not be on bone test. Muscles will be its own separate test. So, but if we have time, we can get a fair amount of that covered. There's only 60 muscles instead of 206 bones and all the processes and all the other things too. So, okay, any other questions? Okay. If not, I'm going to go ahead and go into chapter 24. And this is where we stopped the other day. We were talking about processed foods, refined foods, things with empty calories in it. The things we like to eat because they're tasty. The problem is that foods that are highly refined have a lot of what we call empty calories. What I mean by that is that if you eat something that's full of sugar, and who doesn't like to eat things that are full of sugar? Okay. If you eat something that's it's got a high sugar content, it doesn't take long to break that sugar down to glucose. So our bodies will take a Snickers bar, lots of sucrose, lots of lactose, lots of fats, lots of protein in the peanuts. I mean, it's not a bad snack, but it is easily broken down to glucose. Glucose is the #1 carbohydrate our bodies use. Like, it's the only carbohydrate our bodies actually use. We store carbs in the form, excuse me, of glycogen, but we use glucose. And if it's simple, if it's easy to get the carbohydrate broken down to glucose, then we get a lot of glucose all at once. So if you're eating a Snickers bar, and I like Snickers bars, I'm not picking on Snickers bars, but if you eat a Snickers bar, you get a big surge of sucrose, or whatever maltose or whatever sugar they're using in there. And then that's easy to break down into glucose. But, and so you get this big surge of energy. The commercial, you're not yourself unless you eat a Snickers bar, the old Betty White commercial. I liked it better when she was laying face down in the mud, but that's a whole other point of view. Anyway, you get all that energy released at once. It's almost like having a firecracker go off in your belly. because of all that energy that's coming out. And there really isn't much difference between, the only difference between releasing energy from a Snickers bar and a firecracker is the timing. That's all. It's the speed of the reaction, because it's all the same type of reaction. But if you release all that energy at once, because you're breaking down your Snickers bar, it goes to your cells and you feel perked up and you get excited and you do things and you have a lot of energy, and then you don't. It goes away because you can't keep energy. You can only use it. What if you ate an apple? Apples are boring, I know, but let's say you ate an apple or a baked potato. Apples and baked potatoes are made of the polysaccharide in there, the carbohydrate in them are starches, or maybe you had a plate of spaghetti. They're made of starch. A bagel is made of starch. Even a donut is made of starch. At least the inside of the donut, the outer covering is all sugar. Anybody ever see Krispy Kreme run their donuts through the, it's like, pile on this sugar. I think I said that the other day, but it's still a great, if you've never seen it, you got it. It's great to see. The starch takes time. It's a complex carbohydrate. It takes time to break it down, and you don't get all the energy released at once. And those are better for us. They're not empty calories. They give us energy that is sort of released as we need it, as opposed to this sudden release of energy all at once. And of course, the problem with the simple sugars is you get this big surge of glucose. What does our body do when we get glucose? Well, first of all, we release insulin to get the sugar into our cells. We release insulin. Insulin stimulates the production of carrier proteins in the cell membranes, and a lot of glucose goes into the cell. Well, there's a point where the cell can't handle any more glucose, so it sends it to the liver. The excess glucose gets sent to the liver. The liver stores it as glycogen. And if there's even more sugar, it ends up being stored as fat in the adipose cells. So a diet that's very high in simple sugars ultimately costs us. The simplest cost is we end up with weight gain because we are eating all these carbohydrates. We're processing them, but we can't process them fast enough to burn up the energy. So you eat a couple donuts, and there's nothing wrong with a couple donuts. There's nothing wrong with any food. But you eat a couple donuts and you get all this sugar, and if you do that every day, it's going to catch up. And that's how you counsel your patients. There's nothing wrong with having a cheeseburger. There's nothing wrong with having a donut or two. There's nothing wrong with eating pizza. There's nothing wrong with any of that, as long as it's not excessive. Your patients can enjoy any of those foods as long as they don't go overboard on it, because then we start getting health issues. Now, and I know that this next area, lipids, has always been a big concern. Everybody's worried about, fat content of food and things like that. But it's really the carbohydrates that are going to give us more problems than it is the fats. Carbohydrates are sort of the sneaky little problem coming in there. Now, the second category are the lipids, the fats, the triglycerides, the neutral fats. Why do we like fat? What does fat do for us? Well, it's a great energy source. Carbohydrates only have 4 calories per gram, but fats have 10. So fats are a great source of energy. In fact, our skeletal muscles store fat within the muscle as an energy source. Go down to Food City and look at the beef, and look at the fat around the beef, or look at chicken. You can see, you can still see some fat hanging on to the pieces of chicken there. Muscles store energy in the form of fat. It's concentrated energy. It's twice as much energy as what you get, same amount of carbs. Fat also makes things taste good. The fat content in certain foods makes them creamier and smoother to eat and allows us to enjoy the flavors better. The fat content works like a lubricant, if you will, so that the food particles roll around inside our mouth, come in contact with our taste buds, and we pick up the flavors better. Plus, it's a smoother, creamier surface. Ice cream, for example, ice cream, who doesn't like ice cream? You know, so ice cream is creamier based on its fat content. You know, when you go to Walmart and you see, or Kroger or Food City or any of them, and they have their store brand, their house brand ice cream, but it's called premium ice cream. Premium is not just a term that they throw out there. Oh, it's premium because it costs more. It's premium because that's a measure of the butterfat content in there. The more butterfat content, the better the ice cream tastes. Baskin Robbins has high butterfat. Marble Slab has high butterfat. Any of the house brands have high butterfat. It makes it taste better. So we like fat in our foods. We wouldn't usually acknowledge it, but you know, fat makes things taste better. So the triglycerides are the most abundant fat in our diet. They are the neutral fats. We looked at these earlier in that chemistry section. We have the glycerol is the 3-carbon alcohol, and you have the fatty acid chains sticking off here. And the fatty acid chains contain a lot of energy. All those covalent bonds that have formed between the carbons and the hydrogens represent a lot of potential energy. Remember, the highest amount of energy is in the valence electrons. That's the highest amount of potential energy. That's what we measure in the calorie content of food, the energy available from the valence electrons. So here we see one that is an unsaturated fat because there's a double bond in that third fatty acid chain. You know, we have that term saturated and unsaturated fats. You know, let me get back here before I go on. An unsaturated fat doesn't have every space filled up with a hydrogen that it can hold. You'll notice here, because of the double bond, we don't have 2 hydrogens here. That's significant because that means that that fatty acid will bend at the double bond and you won't get van der Waals attraction there, and that won't be a solid. This will be a liquid at room temperature. This is going to be an oil. Okay, so what do we do with fats? Well, our bodies like fats because fat-soluble vitamins, we can't get them into our body, into our digestive tract any other way. They have to dissolve in fat. They can't get across the cell membrane. A fair amount of our vitamins that we get every day are going to be fat soluble, like vitamin A, vitamin D, for example, vitamin E. Those are all fat soluble. It is the fuel source for our liver cells and for our skeletal muscle. We make our cell membranes out of fats, out of the phospholipids, and we use cholesterol to make hormones. All the steroid-based hormones, the sex hormones, and all of our stress hormones, and hormones that we call the androgens, the generic sex hormones that trigger puberty. We also use cholesterol to reinforce the cell membrane. So we have lots of uses for fat. So how much fat should we take in? Well, less than what the average American takes in now. If we assume a 2,000 calorie a day diet, a person in what we would refer to as a sedentary occupation, someone who spends most of their day not active, sitting at a desk, maybe, I don't know. There's nothing wrong with this approach. Burns about 2,000 calories a day. That's the price we pay every day for living, is 2,000 calories. And generally our diet should replace that and no more. So if we burn 2,000 calories a day and we take in 2,000 calories a day, we should maintain our body weight. However, most people in the United States take, sort of skew that 2,000 calories towards the fatty, the lipid and the carbohydrate side. A healthy amount of fat in our diet should be about 600 calories, 30% of 2,000. 30% of our calorie intake on a daily basis should be fat or lipids. If I say fat, I mean lipids, it's the same thing. So 30%, but most people take in 40%, about 800 calories of fat on a daily basis. Doesn't sound like a lot of difference, but it is significant because it adds up. It adds up in us. And we need to limit our favorite fats, the saturated fats, the ones that are solid at room temperature. We need to limit those to only 10% of our intake. Only 200 calories of that 600 should be coming in saturated fats. What about eggs? Over the past 50 years, eggs have gone from being great to evil, to great to evil, back and forth. Every so often, a new study comes out and says, eggs are good for us. Another study comes out and says, eggs are evil. They want to take over the world, Eggs are the Russians of the world right now, because they're evil. Okay, so I didn't say the Russians are going to say eggs are evil. Eggs aren't evil. The problem with eggs is the yolk of the egg is pure cholesterol. It's like 300 milligrams of cholesterol, which is a lipid. Cholesterol is a pure lipid. And, but we need cholesterol. Now, why do we say that eggs have been evil? Well, up until the 1970s, maybe even in the 1980s, the average American breakfast was bacon and eggs. Everybody ate bacon and eggs. You're getting, fatty meat, because bacon, you fry it up and it has a lot of fat in there. And then of course you have the eggs, which have, the albumin is wonderful. The white part is wonderful, but it's just protein. And then you have the egg yolk, the 300 milligrams of cholesterol. And a lot of people ate that breakfast every day, along with a meat and potatoes meal in the evening. Well, lots of red meat, lots of starches, lots of fat in the morning, and lots of people developed heart disease and died, at 60 or 65 years old. You can, if you ever, I used to teach the general biology class here for the majors. And in general biology 2, one of the things we would do is do a cemetery study. It sounds like really thrilling. And we would go look at death rates, age and death rates of males and females. And the males, up until the 1960s and 70s, the males consistently died younger than the females. And a large portion of it was, there was a big argument back in the 50s and 60s that women don't get heart disease. They're immune from heart disease. Well, that wasn't true. What it was, once women started entering the workforce in great numbers, they started dying as fast as the men did. So it was all based on diet and stress. People that ate these high fat, these fatty meals, high in fat, high in starches, would develop heart disease. That's the problem with a high fat diet, along with a high carbohydrate diet. Cardiovascular disease is still a problem in the United States. Heart disease is still a problem. However, the amount of people dying from heart disease in the United States every year has pretty much leveled off somewhere around 800,000, 500 to 800,000 people, which is about the same number that were dying back in the 1970s. But our population has doubled. We had about 180 million Americans back in the 1960s and 70s, somewhere in there, maybe 200 million Now we're about 330 million, and yet the same number of people are still dying from heart disease. So something's working there as far as the percent that are actually dying from heart disease is dropping down. But these meals that are high in fat and high in carbohydrates cause significant health issues in your patients. And the Southeast is like ground zero in all this stuff because, you know, Tennessee, we have major issues with heart disease and hypertension and diabetes and obesity, and it's all sort of rolled in together. Obesity leads to diabetes and heart disease. Heart disease leads, is a result of hypertension. Hypertension causes heart disease. Obesity causes hypertension. Diabetes is a result of obesity, and it causes hypertension and all sorts of other nasty things you'll see in AP2. And so it all comes together. The blame can all be placed to a large extent on diet. Okay, now, sources of fats, animal fats, lard, meat. Lard is rendered animal fat. What do we use lard for? We use it as shortening. Best pastries, best pie crust, best pastry shells, best biscuits come out of using lard for shortening. It produces a lighter, fluffier texture. Because of all the fat there, it tastes good. So make a biscuit without any kind of lard or shortening, and you're going to have a hockey puck. We have animal fat in meat. Even when you trim it off, it's still there. We have animal fat in poultry. We have the cholesterol in eggs. We have milk fat, milk products. Now, milk gets a very bad name here also because milk, whole milk is considered, oh, that's evil too. It's lined up with the eggs. They're going to take over the world. But whole milk is only 4% fat. Think about that. If you buy a bottle of whole milk and buy a bottle of skim milk, you've lowered the fat content by 4%, from 4% fat to 0%. 1% fat or 2% fat is not that much of a significant difference from whole milk. So just to keep that in mind, but it's still a source of fat. Plant sources of fat. Chocolate is a source of fat. Corn oil, soybean oil, cottonseed oil, and olive oil are sources of fats. These are unsaturated fats. Corn contains fat. Plant seeds, like if you like sunflower seeds or pumpkin seeds or anything like that. Peanuts, pistachios, all this contains fat as oils, but they are unsaturated fats. These are healthier oils. Now, some people get cholesterol by eating organ meat. Anybody like to eat livers? Anybody ever eaten the liver? Chicken liver?
What kind of liver? I had it in Ukraine, but it was not good.
Okay. Well, I can remember being forced to eat beef liver when I was a kid, and eating turkey liver at Thanksgiving, and that was fine until I found out what livers do for us, and I don't eat it now. Yeah, it has a very strange texture. It's what was the word? What was the word for the texture?
It's gross.
Thank you. That was the word I was looking for. It has a gross texture. It's almost like a vegetable or a fruit texture, except it's a meat, and it's
not.
The only good thing about liver is the onions that are served with it, you know. So now, some people like to eat kidneys. In England, kidneys are very, very popular. Some people like to eat brains. Seriously, and they're not zombies either. So, but brains are considered a delicacy, particularly mixed with eggs. So, of course, cholesterol comes from egg yolks. If you like to eat fish eggs, you get cholesterol. Who likes shrimp? Okay, you don't like shrimp? Okay, what about crab meat? Lobster? Okay, that's fine. You know, all of that is very high in cholesterol. Just because it came out of the water doesn't mean it doesn't have some surprises in there. So we have sources of cholesterol in a lot of things we eat. Is cholesterol bad? No, we have to have a certain amount of cholesterol every day. If we don't, our bodies are going to make it. You can't go cholesterol free and assume your cholesterol levels are going to drop. Our bodies need that cholesterol. That's how we make our steroid hormones. The sex hormones are all made from cholesterol. Our stress hormones, the hormones that regulate our fluid levels in our bodies, and our salt levels are all based off cholesterol. We have to have cholesterol. Someone that says, I'm never going to eat cholesterol again and I'll be extraordinarily healthy. Well, no, your body's just going to go ahead and make it. So we have to have fats. We have to have fats in our diet. We have to have cholesterol. In there we make the hormones. It reinforces our cell membranes. It makes the bile that breaks down fat in our small intestine, made in our liver, stored in our gallbladder. Someone that has had their gallbladder removed still is going to be producing bile. You know, lots of people say mistakenly, well, I had my gallbladder out, I can never eat fat again. It's not true. The liver makes the bile that breaks down the fat. So we use fats and cholesterol all the time. We store fats in our body for energy. We use fats to protect our organs. Many of our organs in the viscera have no protection other than a cushion of fat around them. In last week when we were dissecting the cow hearts in the AP2 labs, and you all will get a chance to do that in AP2, the cow hearts, well, first of all, they were massive. They were about 4 times the size of a human heart, but they were covered with fat. Yeah. Cows don't worry about their cardiovascular condition, but they had lots of fat. We had to cut through a lot of fat to open up the heart. And that's what a human heart would look like that is not exercised and fed properly. An individual with heart disease often has a great deal of fat stored around their heart. I can tell you that a number of years ago, we took a group over to Pellissippi to their cadaver lab, and we were opening up an older male that had died from heart disease, and his heart was about the size of a football. Now, the normal human heart is this big, fit in the palm of your hand, size of your fist. And this individual's heart was about the size of, as I said, about a football, covered with fat. And it was, you know, it was from a educational perspective, it was fascinating. It's really sad though to think that this person had died because he didn't take care of himself, you know. And it's when it comes to our dietary intake, it's easy for us to not take care of ourselves. You can't, it's hard to criticize someone like that. Now, so fat, in addition to all the other good things it does for us, it also stores energy, it insulates us, it keeps us warm and keeps us cool. It protects many of our organs. Our kidneys set up high, right up here, right below the ribs, with no protection except a big cushion of fat. All of our viscera, everything below the diaphragm, has layers of fat around them to protect it because there are no bones to protect the stomach or the pancreas or the liver or the spleen or the small or large intestines. So we have layers of fat around it to protect it. And skeletal muscle packs in fat because it's high in energy. The skeletal muscle will use that fat. You know, as I said, a gram of fat has 10 calories of energy as opposed to just 4 calories per gram of carbohydrates. Now, in our bodies, we eat fat and we process it, and it goes down to our small intestine right over here. The first 10 inches or so of our small intestine is called the duodenum. Don't worry about that now. And that's where we finish processing proteins and processed fats. We chop up the fats into little tiny pieces here. We will take the triglyceride and slice it up into the separate fatty acids and leave behind the glycerol and one fatty acid. So we have the monoglyceride. We chop it up so that we can transport it. In fact, the bile from our gallbladder acts very much like dishwashing liquid. You know, dishwashing liquid breaks up fat particles and breaks up the grease. Well, that's what the bile does. It chops up the fat so we can transport it in our lymphatic system. And the transport for the fat, we take it to the liver. The liver processes the fat. The fat and cholesterol then get sent out to the cells using the low density lipoproteins. That's the LDL, is what we call the bad cholesterol. Because the LDLs take the fat, take the triglycerides, and take the cholesterol out to the cells. And what the cells don't use, the rest of it accumulates in our arteries and around our organs. Now, the other type of lipoprotein, the HDL, the high density lipoprotein, the good cholesterol, brings that excess cholesterol and excess fat back to the liver for destruction. And that's what we like. We don't want to have high levels of cholesterol accumulating around our organs in our blood vessels. This is what over here on the left, this is what it looks like. This is a coronary artery. And what will happen is that the fat and the cholesterol will form these deposits called plaque, and they will narrow the coronary artery. And this condition is known as atherosclerosis, or common term you probably heard of, hardening of the arteries. Lots of people call it that. It's called atherosclerosis, and we accumulate plaque around these coronary arteries. And yeah, I waited for almost an hour before I got my pen out, so maybe I'm getting better. This plaque fills up, perhaps I should change the color. This plaque fills up the artery and narrows it. And then what will happen is a clot will form. Maybe a cell will bounce against this and stick, and a few more will stick. And pretty soon you have a narrow artery that gets blocked by a big clot. And that's the cause of a heart attack in the heart or a stroke in the brain. It blocks the artery. So, and that's a major health concern. Now, something else that happens, so you got a risk of heart attack from heart disease. You also have a risk of stroke in the brain, maybe even hypertension, high blood pressure. There is another problem with taking in fat from different sources. There's a disease known as Creutzfeldt-Jacobs disease. It is the human version of bovine spongiform encephalitis, what we call mad cow. Now, how many people get Creutzfeldt-Jacobs disease a year and die from it? About 3 people every year. Not a lot of people get it, but it is out in the population. The other, and how does it get spread? It gets spread by eating infected organ meat. You can't cook the agents that kill this disease. You can't destroy them by cooking. They're resistant to anything. And this Creutzfeldt-Jacobs disease has been around for a long, long time, but it was in very small, very obscure locations. It used to be found in a cannibal tribe in New Guinea, off the coast of Australia. Very few locations. And then somehow, when mad cow made the jump into humans, it was the same condition here that caused this. We have a significant concern about this in Tennessee. There is an animal version of this. It shows up in deer called chronic wasting disease. I don't know if you ever heard of this or not, but this is why when I came to Tennessee in 2004, there was no problem in the state with chronic wasting disease. Other states had it, but Tennessee didn't. Now it's showing up all over the state. And if you eat deer meat that the deer is infected, the deer had chronic wasting disease, you run a very high risk of developing Creutzfeldt-Jacobs disease and dying from it. There's no cure. The brain shrivels up. This is if you look at the picture of the two cross sections of the brain, a healthy brain on the left and a chronic wasting disease, Creutzfeldt-Jacobs disease brain on the right. You can see how the brain shrivels, and the holes in our head, and we have lots of holes in our head, we really do, but they have a purpose there. They get bigger and bigger, and the person stays aware of their condition almost to the end. And they're very much aware of losing their intellectual capacity and their ability to do things. They're very much aware. They can't do anything about it. So it's a very unpleasant disease. No, I don't think anybody has ever died from mad cow, from eating infected cow meat. I know they have in England. England had an outbreak of mad cow about 20 years ago, and they had to destroy their entire cattle population, killed them all so that people wouldn't get infected, because you don't know who's going to, the cows, you can't tell. So you kill everything.
Is that why they ask you when you go make blood, like you or your parents would?
Yeah, because you don't know how it's going to get spread. Part of the problem too is that it's usually meat around the nervous system. So these structures called prions tend to inhabit the nervous system of the animals. And so what part of a cow do we like the best? The ones that are closest to the nervous system, T-bone steaks, for example. Or do you like hot dogs? You don't like hot dogs? Okay, so I'm not going to destroy anybody's we can have a steak. All beef hot dogs, they don't tell you, and I like hot dogs too. All beef hot dogs don't tell you what part of the cow they came from. It could be any part. It could be the leftover meats from along the side that are infected. So it isn't that you should just, well, I won't eat T-bones, darn, I won't pay $15 a pound for a T-bone, well, but if you eat hot dogs, so there's a risk there too. So anyway, I know in Tennessee, we're very much aware of chronic wasting disease. And so there's restrictions on bringing deer meat from other parts of the state. There's restrictions on where it gets processed. So, okay, now. Fat substitutes. With all this concern about fat, there's always a desire to do something better. Fat substitutes. If we can avoid the fat, we can avoid the calories, we can avoid the complications here. The oldest fat substitute is air. You can whip a product together and make it lighter, and it will still taste okay, tastes good. Whipped cream, for example. Whipped cream is nothing but air and heavy cream, the high fat cream, but you make it go from a small container of cream to a big bowl of whipped cream, or in the can. My wife makes homemade whipped cream all the time. It takes about 10 minutes with the beaters on high, and it's fine. You're just substituting air in here for less fat. The other products that can be used, different types of starches, different types of gums, not quite like the gum we have in chewing gum, but it is still a sticky substance. It gives it texture. Whey protein, product from making cheeses. There are all sorts of products that can be used in ice cream. Ice cream has seaweed in it. There's a product known as carrageenan. It comes from seaweed. It helps to give ice cream its texture. We eat it, don't even know about it. There's all sorts of stuff. The only thing wrong with all these fat substances, they still provide calories. It's not beneficial in that aspect. So along comes Frito-Lay about 20 years ago. Frito-Lay developed a chemical substitute for fat. It was called a sucrose polyester. It was a synthetic fat that would provide all the benefits of fat without being absorbed. Now, there were a couple of problems with this product. The first problem was that it broke down at 300 degrees, so you couldn't fry with it, couldn't cook with it. It was too temperature. It wasn't stable above 300. The other problem, and this they didn't know until they put everything out into production, they had a whole line of potato chips and pretzels and crackers and Doritos and Pringles and all this other stuff based on this synthetic polyester. And they thought, this is going to be great because we are going to have the first snack food available that's not, you can eat without guilt. If you get guilty eating potato chips. Do you like Pringles? You like Pringles? Yeah, who doesn't like Pringles? And they make Pringles with this stuff. And it was going to be great because then you could eat a whole can of Pringles and not feel bad. Well, it turns out that, and they marketed this thing under the name of Wow. That was the product line. The trade name for the product was called Olestra. And here you see Wow over here. Fat-free potato chips, half the calories. The only problem with the fact that Olestra wasn't being digested was that it caused in about 35% of the population, it caused explosive diarrhea with no warning. In about 35% of the population. Look at the individuals there next to the Pringles smiley face. That it is so appropriate there. The warning on the can that came out after several months was Olestra may cause abdominal cramping and loose stools, another name for explosive diarrhea. It inhibits the absorption of some vitamins and other nutrients, meaning all the fat-soluble vitamins like A, D, E, and K can't be absorbed. But the biggest problem was that it caused this massive cramping and explosive, without warning, diarrhea. So anyway, about 3 or 4 years ago, every now and then, and I'm in, one of the grocery stores around town, I'll look and see if they still have these. Up until a few years ago, Kroger still had the Olestra Pringles, but I haven't looked there lately. I know that I can't find them at Food City anymore. Haven't looked at Walmart. I try to avoid going to Walmart. That's another story. But I haven't seen them at Kroger. So I don't know if Frito-Lay took it off the market or not. But for the people that, if you were an individual and you were trying to watch your fat intake and you didn't have a problem with it, then it was a good thing. It's like the people that like to drink Diet Coke with saccharin in it. Saccharin was the first big artificial sweetener, and it was taken off the market back in the 80s because it caused cancer in the tails of rats in Canada. Yeah. Now that rat, to get that cancer in their tail, have to drink about a case of Diet Coke with saccharin a day. I know people that drink Diet Coke like to go one can after another, but first, you're not going to drink a whole case a day. And second of all, the cells that the cancer showed up in the rat weren't in humans. So anyway, okay, so it may still be out there. I don't know. Someone gave me a can of pizza flavored Pringles about 6 or 7 years ago, but I haven't seen them since then. So, now, what about proteins? Proteins show up in our diet. Obviously, we get them from animal protein and plant protein. The animal proteins are complete proteins. The complete proteins, meaning they have every one of the animal proteins has all of our needed amino acids. All 20 amino acids are in every one of the animal proteins, whether it's chicken, fish, dairy, cheese, I guess that's dairy, eggs, all this. Anything from an animal source is going to have all 20 amino acids in their protein. Plants don't give us all 20. Different types of different amino acids show up from different plants. So to get the 20 amino acids we need, because there's only 20, to get the 20 that we need, if you want to make sure you get all your amino acids, you mix and match. You eat beans and rice, or beans and corn, something like that. And that will give you everything you need. That will give you the 20 amino acids you have to have. Or, if you eat cheese or chicken or fish or beef, and you get all 20. We know that we have to have protein in our diet. We need it for the keratin that waterproofs our skin, the collagen fibers, the elastic fibers. Our muscles are made of protein. Now, our muscle cells will never reproduce, but they will get bigger or smaller based on the demand placed on them. And they'll get larger by adding more protein, or they'll get smaller by using up that protein. So we have to have protein in our diet. We have to be able to make enzymes. We have to be able to make antibodies. We have to be able to make hormones. Most of our hormones are made of proteins. There's only a handful of hormones that our bodies use that are made from steroids. Most of them are based off of protein. So how much protein a day do we have to have? Well, you could sit there and do the calculation if you want to, but a pretty much standard amount is about 50 grams per day. 50 grams of protein is what meets our needs. And you can get that in a variety of sources. I think that if you look at the nutritional ingredients on a Whopper or a quarter pounder, for example, both of those are close to 50 grams of protein in there, based on the meat that's involved. It's about 50 grams a day. That becomes no problem in the United States. It becomes a big problem in many other countries. So now, proteins follow what we call an all or nothing rule. When we do protein synthesis, for protein synthesis to work, we have to have all the amino acids necessary. We can't make a protein and get up to position number 452 and say, oh, where's the valine? It's not here. And we can't, we won't even try to make the protein if we're missing the amino acid. So we have to have every amino acid present. We also have to have energy for protein synthesis to occur. And if we don't have enough energy for protein synthesis, we'll start breaking down existing protein and converting it to glucose. Remember the term gluconeogenesis, the creation of new glucose we convert, glucose, new glucose, genesis is creation, gluconeogenesis. We make glucose from fats. We make glucose from protein. If we don't have enough energy to build the proteins we need, we'll break down we'll burn through the carbs, then we'll go through the fats, and then we'll go through the proteins. Which is why it takes, a person can go without food for about a month. Another term here, nitrogen balance. The rate of protein synthesis in a healthy individual, how fast are we making proteins, is equivalent to how fast we're tearing them down. So we are in like a zero-sum relationship. We make proteins and we're tearing them down, or they wear out, and we're in equilibrium on that. We can be in positive balance if we are making proteins faster than we're tearing them down. Kids are like that because kids grow. If you feed them, they're going to grow. And they will grow rapidly at different times. And the protein synthesis that's taking place is much more rapid than their breakdown. So children are usually in a positive balance. We can be in a positive balance if we are repairing damaged cells too. But we can be in negative balance if we're under a lot of stress. Negative balance means that we're breaking down proteins faster than we're making new ones. We can be under a great deal of stress. We can be dealing with severe burns or injuries. We maybe have poor dietary habits. You may be dealing with a patient who only eats one thing all the time. Maybe they are obsessed with Frosted Flakes, and that's all they eat is Frosted Flakes 3 times a day. People get like that. Or they only eat peanut butter, or they only eat whatever, or maybe they don't eat anything. One of the big problems with older people, with elderly people, is they lose their sense of taste and they lose their sense of smell as the taste buds wear out and as the olfactory receptors wear out. So things don't smell, they don't detect odors, they don't taste food. And many older people will say, well, that doesn't taste like it used to, and they won't eat. And so malnutrition often occurs in older individuals simply because the food doesn't taste right anymore. And so if it doesn't taste right, if they can't add enough seasoning to it, then they won't eat it. And so they don't. And so they're in negative balance too. Something else about proteins, our hormones control most of our proteins, particularly the sex hormones. Sex hormones drive the production of proteins when we hit puberty. When we hit puberty, we grow, we hit our adult stature. So the sex hormones drive the stimulus of growth hormone, which tells our long bones to grow. We lay down protein in the bones there, and they enlarge, our sex hormones enlarge our muscles get bigger. We assume our adult body shape, all the secondary sex characteristics appear in males and females, driven by the release of growth hormone, the release of testosterone and estrogen. So we have a lot of drivers that are going to stimulate, that are going to control protein synthesis. Now, here's the makeup. Here's the key on incomplete proteins. Probably have the slide in the wrong spot, but it's okay. You look at the 2 types of food here. We have the cereal grains. We have the corn or rice or wheat or oats or whatever. And you can see that the corn represents 6 different amino acids found in corn. Tryptophan down to leucine. So we see, here we go. So we have tryptophan down to leucine from corn. and valine down to lysine from beans. And yet we need all of those. So if we have a diet of beans and corn, or beans and rice, or any cereal grain and any legume, beans and peas and stuff like that, are going to be a legume. So any combination of those two will give us all the amino acids we need. And some of the healthiest societies around the world have a mostly, legume and grain diet, beans and rice, beans and corn. It's a very healthy diet. Low occurrence of heart disease and hypertension in those societies. Anyway, so if you have a patient that you are counseling about, perhaps they're a vegan or a vegetarian. I really don't know the difference between that, but I know there is. But to get their proteins, they have to eat the right combinations of foods. And this grains and legumes seems to solve the whole problem on that. So, okay, now, vitamins. Many of us take vitamins. Vitamins are a good thing. Many vitamins come in our foods. What do we use vitamins for? They are coenzymes. They allow an enzyme to do its job. They make the enzyme work properly. They are not assistant enzymes or wannabe enzymes. Only the enzyme functions like that. But what they do is the vitamins will help the enzyme. Now, all of our vitamins generally get taken in our diet. Vitamin D can come in through our diet. Vitamin D is also made in our skin. Exposure to ultraviolet radiation allows us to manufacture vitamin D. Vitamin D is absolutely essential because vitamin D allows us to absorb calcium in our small intestine, and we need calcium for our bones and for muscle contractions. Vitamin K, which helps to control blood clotting, is manufactured in our large intestine. But the rest of them, the B vitamins, the C vitamins, the E vitamins, the A vitamins generally come in our diet, or we take multivitamins here. Beta carotene, found from carrots. Beta carotene is what makes carrots orange. Beta carotene is converted to a pigment in our eyes called rhodopsin, and it enables us to have good night vision. The rods, the structures in our eyes, and we have two types of photoreceptors in our eyes. We'll get into that. We get into later on in the semester in lab. But the rods allow us to detect peripheral vision and dim light, things in dim light. The cones give us bright light and color vision. So the pigment rhodopsin is found in our rods, so we have good night vision. We get that from vitamin A. We get vitamin A from eating carrots. The old thing when we were kids, eat your carrots, it's good for your eyes. There's usually some reference to rabbits in there too about carrots. But there is a truth in that foods that contain beta carotene are going to give us vitamin A. Now, there is a limit. It isn't like, well, you ate 3 carrots, you can eat 6 more. You can't. There's a level to how much beta carotene you can take in and have any kind of beneficial effect. But we use beta carotene for vitamin A. We use vitamin B and B12 for the production of red cells. Vitamin C is an antioxidant. It breaks down the free radicals. Vitamin D, we use that for calcium retention. Vitamin E helps us also with blood clotting. There is no one food source, though, that gives us every vitamin. In fact, if you've ever gone looking at multivitamins, you know that sometimes you're picking the lesser of several evils because there is no one bottle of multivitamins that gives you everything you want. If you're looking for iron, it's hard to find a good multivitamin that also contains iron and iodine and lots of B12 and things like that. So you have to sort of pick and choose which is going to give you what you're looking for. And while these are, these multivites are good, there are many different varieties out there. The one-a-day brand is good. Some of the generic brands are good. You have to read the labels and decide what you're looking for, what you tell your patients to take. It is somewhat of a challenge. So my wife and I have ended up taking the one-a-day women's vitamin because that's the only one that has iron in it and iodine and B12. And since my wife is slightly anemic, she needs the B12 and the iron. And I said, well, why not? So it's easier to have one vitamin and we take it every day. But it is hard to find one that's just going to have everything you need. The problem also is that many of these vitamins, they're either going to be water soluble or fat soluble. Now, water soluble vitamins, and you can take as much as you want. You can take vitamin C tablets all day long, and that's great, except your body's only going to use what it needs. All of our water soluble vitamins are our bodies are going to take what we need, and the rest is going to go down the drain. You're going to pee it away. So if you take 10,000 milligrams of vitamin C, because you read somewhere, not you, but your patient, I read somewhere that they won't get a cold, or it'll fight COVID or whatever else, or it does. Well, it will do. Vitamin C is good for us. It destroys free radicals. But once we get past that first hour, it doesn't matter how much we took in of any water soluble vitamin, the rest is going to go down the drain. We're not going to get any benefit from it. Water soluble vitamins don't get stored. So it's a waste. It's a waste of your patient's money to make a dose. It was thought back in the 1960s that that megadoses of vitamin C were going to be the cure for the viruses that caused head colds. It isn't. It makes you a little healthier, and maybe that helps fight off an infection, but that's all. And even certain types of vitamins, like vitamin B12, requires another protein released in the body to be absorbed. It isn't that B12 is going to go right through you. Your body's going to take it at once, but only if it has this substance called intrinsic factor. Excuse me. Intrinsic factor is the only way we can get B12 in our diet. So, and B12 is essential for making red blood cells. So, now what about the fat solubles? They get absorbed across the membrane because they're soluble in fat, and they get stored. And excessive intake of fat soluble vitamins becomes dangerous. Too much of a good thing becomes very dangerous. These megadoses of vitamin E, for example, can affect our ability to clot. It can interfere with our ability to clot when we have an injury and we're bleeding. And so we may become more likely to bleed uncontrollably if we have excessive levels of vitamin E, but it's a vitamin, it's supposed to be good, it can't hurt us, right? No, actually high levels can. High levels of vitamin K can cause us to clot more easily. So again, here, I'm taking a mega doses of a multivitamin with lots of K and E and C and D, and you've got all these issues going on here. Now, one of the benefits of our vitamins, whether it's, and here we see C, E, and A. These are antioxidants. They get rid of free radicals. A free radical is a molecule or a fragment of a molecule that has broken apart from its parent molecule, like a glucose molecule has split into a segment, or maybe some protein has split into a small fragment, and it has acquired a charge. Glucose isn't supposed to have a charge. Water is not supposed to have a charge on the water molecule. But suppose the water splits into the hydrogen and the oxygen. Hydrogen is supposed to be positive, but suppose the hydrogen becomes negative. It's a free radical. It's not supposed to be like that. These radicals will move through healthy tissue and destroy them. They will destroy them through oxidation. The antioxidants prevent this. So we take these multivitamins, or we eat leafy greens, we eat broccoli or cauliflower or Brussels sprouts if you like them. You might eat spinach. You might, if you like spinach salad, or other types of these, spinach or kale or something like that. All the things that nobody liked when they were little kids that are actually pretty tasty now. Chocolate, dark chocolate is an antioxidant, by the way, and so is red wine. You might argue that dark chocolate and red wine is probably a little more interesting than eating some raw broccoli, but that's just whatever. Anyway, the point is that vitamins usually come, we can take multivitamins, that's fine. We get a lot of vitamins in our diet. The water solubles that we will get rid of. We have to be careful with the fat solubles. And so you counsel your patients, don't take mega doses. And of course, the minor nutrients, the other ones are the minerals, the ions, the calcium, the phosphorus. We need that for bones and teeth. Potassium. Potassium is the number one ion found inside our cells. Sodium is the number one ion outside our cells. We have to have iron for red blood cells, for hemoglobin to carry oxygen. We need to have iodine for our thyroid to function properly. We get iodine from salt. Our thyroid won't produce thyroid hormone to regulate our metabolic activity unless we have iodine. We also depend on sodium to maintain our salt balance inside our plasma. Now I'll tell you, chlorine, because sodium comes from sodium chloride. The chloride doesn't get to do a whole lot. It's just there. It's not a major player in any of this. Okay. Metabolic activity. What's going on inside our cells? Metabolic activity are the chemical reactions that allow you to break down foods, to break apart proteins to the amino acids so you can reuse those amino acids for yourself. It allows you to break down carbohydrates to glucose so you can then make ATP from the glucose. It allows you to take amino acids and build them up into a new protein. These are metabolic activities, and we are either an anabolic reaction or a catabolic reaction going on. Anabolic reactions make large molecules from small ones. We take glucose and we store it as glycogen in our liver. Glucose is nothing but glucose molecules linked together. Thousands and thousands of those linked together give you glycogen. In plants, it would be starch. Plants make glucose and they link them together and they store it as starch in their leaves and in their roots. If you eat a potato or a carrot, you're getting starch from the plant. That's an anabolic reaction. If you exercise and work out and you eat protein and your muscles get bigger, those are anabolic reactions because you're making more and more protein for your skeletal muscle. The muscle cells enlarge. Catabolic reactions are taking large molecules and breaking them down to simple ones. little ones, usually carbon dioxide and water. If you oxidize, if you burn something, if I light a match, this is a catabolic reaction. I'm releasing the stored energy in the chemicals at the head of the match and in the wood, and I'm releasing carbon dioxide and water. So I take a large complex molecule like the cellulose and lignin in the wood and the chemicals surrounding the head of the match and letting them release their energy. They represent potential energy, letting them release their energy, and I end up with carbon dioxide and water. So complex, large molecules are broken down into smaller molecules. That is metabolic activity. Anabolic reactions. We take glucose and turn it into starch, into polysaccharides, into glycogen. Or we take a disaccharide here. We don't make glucose. We don't make sucrose. We would take two glucoses and link together to make glycogen. But an anabolic reaction is always going to make a bigger molecule from small ones. So, two monosaccharides linked together will give you a disaccharide. That is two small molecules giving you a bigger one. Amino acids linked together gives you a protein. Those are small molecules linked together to give you a protein. These are anabolic reactions. Anabolic reactions always require energy. It takes energy to link those small molecules together. Catabolic reactions release energy. We break down the carbohydrates, we break down the lipids, we break down the proteins, and we release energy. Remember, every gram of carbohydrates has 4 calories. Every gram of fats has 10 calories. If we break down the fats or break down the carbs or even the proteins, we're going to release energy. Like lighting a match, striking a match and lighting it. That is a catabolic reaction. We release the energy. We take a large molecule and convert it to a series of small molecules, and we've released energy. The energy that we release comes off as electrons. When we're releasing the electrons, we are releasing energy. Now there's a term here that you're not going to like this term. It's going to fall into the same category as chemistry. I don't know how much you like the chemistry chapter, but there's only a little bit of it here. Cellular respiration. Cellular respiration is not breathing. Cellular respiration is the breakdown of food, the fuel that we take in, the carbs, the lipids, the proteins, the breakdown of food that we can take the energy from the food, the calories in the food, to make ATP. ATP is our currency in the cells. We can't take the energy straight from glucose. Can't take the energy from glucose and bring it over to the cell and say, here, do something. Go do good. It doesn't work that way. We can take the energy from glucose and put it into an ATP molecule. The ATP molecule can then go and release that energy at the site in the cell where it's needed. There's too much energy in a molecule of glucose to be released at once. We can't release all that energy at the same time in a location in the cell, because it would be like taking my lighter and I want to get my finger I want to exercise my wrist, so I'm going to hold this flame underneath my wrist so it'll work faster. It doesn't work that way. There's too much energy here in the fuel in the lighter that the cells can handle. I'd be better off, eating some protein or some carbohydrates, and that's how I would do it. So now, how do we get cells to take the energy from glucose. It comes down to phosphorus. There is a, ATP, adenosine triphosphate has 3 phosphate groups attached to the end. The third phosphate, number 3 here, is held to the other 2 with what's known as a high energy bond. If we have adequate energy available, we can form ATP from adenosine diphosphate, the 2-phosphate structure, and an inorganic phosphate. We can force that third phosphate on there, and that high energy bond will hold that phosphate for us. What we do is we simply are shifting these phosphates around. We're either taking them off of a molecule or putting it on. We're either busy releasing the energy from ATP, or we're taking the diphosphate version and inorganic phosphate and storing it. So it looks something like this. Here is ATP with its 3 phosphates here, and we break this bond, release energy. Energy comes off. Now we have this, phosphates 1 and 2, and we have phosphate 3 out here by itself. But if we add energy, we can join that together. And so this is what we do with ATP in our bodies all the time. We're either adding the third phosphate, storing energy at that high energy bond, or we are breaking it. Now, the problem with ATP is it only lasts 7 seconds. So we have to keep making it over and over and over again. But using the energy from our food, we're busy making ATP, and we are breaking that bond when we get to do something with it. For example, the ability to contract our muscles depends on the presence of ATP. So if we want to do something with our skeletal muscle, we have to have ATP there to allow our muscles to contract. No ATP, no contraction. And we keep making as long as we've got glucose, we can continue to make lots and lots of ATP. So let me clear this. So the key term that you'll want to remember is phosphorylation. Phosphorylation. Okay. This is a good place to stop. In here, we will pick up with this and wrap this up on Thursday. And maybe I'll even get to do some real science while we're here. So, okay, let me get out of here. Anybody have any questions on any of this before I pull the plug? Don't tell me you have a question.
No.
Okay. Okay. So, well, I mean, it's okay if you want to stretch. That's fine. In another couple of weeks, you'll be able to tell me what chemicals are involved in that stretching process. So, anyway, lab this afternoon, we are going to take a look at joints and articulations, and then we're going to take a look at. I want to introduce you to the skeletal muscles. So. And if you're going to be on campus, that's great. If not, you'll still see it on Zoom. So I'll get us out of here, and I will see you in lab.